Math 1332, Chapter 10, Probability and Counting Techniques. Section 1, Basic Concepts of Probability. Video 6, where have we seen all this before? Full disclosure, the content of this video is not going to be assessed. So I get the feeling some of you are going to stop watching it right now. But some of you in the future may need to take statistics. And you're thinking, not me. I got a surprise for you. If you get your bachelor's degree and decide to pursue a master's degree in whatever area you pursue it in, you will probably have to do some research. And that research will probably involve processing some data. And that data processing is almost always done with statistics. So a lot of people who get graduate degrees, not knowing in advance, are required to take a statistics class. Now, sometimes it's just a how to use a statistical computer package class, but in my opinion, statistics is one of the best math classes for people to take because it has such a universal appeal in a wide area of majors. Even if you don't use it as the primary tool, it's important to understand statistics. So why am I bringing this up? Because if you do have to take a statistics class in the future, the more perspectives you have on how to approach things, the better. And by the way, statistics revolves a lot around probability. So the purpose of this video is to give you a visual that you may carry forward if you have to take a statistics class. Plus, internal to this class, it kind of goes full circle because it takes us back to set theory, which shouldn't really surprise you at this point if you've been listening. Throughout this series, I've made casual, not causal, casual. Causal means something totally different. I've made casual allusions to past content, in particular set theory. In fact, I've even connected current content to symbolic logic. Remember the video where I brought up the law of contraposition? And even consumer mathematics when we convert between fractions, decimals, and percents, which we do quite a bit, or which we could do quite a bit with probabilities. But I'd like to focus a little more on the connection between probability and set theory. By definition, a sample space is a set. It's a set of all possible outcomes for a probability experiment. Specifically, oh, I just said that. It is the set of all possible outcomes for a probability experiment. In case you're wondering, I type these from my own head. I rarely ever copy other people's notes. So it's not a surprise that the things I say off the top of my head match the thing on here, and I'll look at it and go, oh, that's exactly what I said. So let's start over. By definition, the sample space is a set. Specifically, it is the set of all possible outcomes for a probability experiment. As such, it is like a universal set. An event is a subspace of a sample space. Excuse me, subspace. That's way beyond this course. An event is a subset of a sample space, and both of these can be illustrated with the Venn diagram. In fact, let's do that for a specific example earlier in this video series, where we had a sample space of 1, 2, 3, 4, 5, 6, 7, and our event was 1, 2, 3, and 5. We can easily draw a Venn diagram for this by labeling the universe as S and drawing a circle for our event, and put the elements of the event, the outcomes, inside that circle. 1, 2, 3, 5. But if we're going to draw a Venn diagram and represent the elements inside of it, we need all elements of the universe represented. Oh, I'm sorry, all elements of the sample space. So first off, which numbers are not yet represented in the Venn diagram? Well, all numbers except 1, 2, 3, and 5. So 4, 6, and 7 have yet to be represented. Where do those go? Outside the circle. Anywhere you want to put them, we'll put the 7 over here. Wait, 4, 6, and 7, those are the numbers outside the circle E. Those are the outcomes not in event E. What does that make the set 4, 6, 7? Well, that's easy. The set 4, 6, 7 is the complement of E. From both a set theory perspective, all the elements in the universe not in E, And from a theoretical probability perspective, all of the outcomes from the sample space that are not in event E. But it goes a little bit further than this. Based on this picture, we can now calculate probabilities fairly easily, because the probabilities are based on cardinalities. Probability of E is the cardinality of E over the cardinality of S. Well, if the elements are in the Venn diagram, I just have to count. Cardinality of E means how many elements inside of circle E, that would be 4. Cardinality of S means how many numbers in the rectangle altogether, and that would be 7. And I can do the same thing with the probability of E complement, which is the cardinality of E complement divided by the cardinality of the sample space, which is still 7. But where is E complement? Do you remember visually where the complement of a set was? The complement of a set was outside of it. So E complement is everything out there. How many elements are in the part that I highlighted? Careful, it's not 4. If you said 4, then you are looking at this guy, but that's not an element, that's the name of the set or the name of the event. The number of elements in the set, there's 1, there's 1, and there's 1. So there are 3. If you wonder why I keep bouncing, it's because I'm tapping on my screen on my laptop and the screen just goes back and forth. But anyway, there are 3 elements in E complement because there are 3 elements outside of the circle but still in the universe, and so that probability is 3/7. There is a much, much, much deeper connection between probability and set theory, including unions, including intersections, and I want to say even including set difference. But we may or may not get to some of those things, but just to let you know, there is a very strong connection between all of those things.